Dear colleagues, on behalf of the co-authors, I will present the paper with the title Research and Justification of Running Wheels Tire Parameters of Bridge Type Transport Energy Vehicle. Improvement of agricultural technology is inextricably linked with the introduction of innovative technologies, which should include track and bridge farming. The essence of it lies in the fact that to achieve high traction and traction properties of the vehicle, its propulsors must have contact with a dry and solid supporting surface of the transport path. Furthermore, and for normal growth of cultivated plants, an optimal moist and loose environment is needed. Practically, such requirements can be satisfied only when clearly delimited in the field between the zones of traffic for bridging energy vehicles, technological field zones, and plant growth zones, agro-technical field zones. The process of rolling the wheel of a bridge transport vehicle with an elastic rim on a compacted aligned track of a constant technological track is characterized by the expenditure of energy to overcome the forces of resistance. At the same time, the main objectives of the rolling of the bridge vehicle wheel on the soil track of a constant technological track are the identification of the relationship of its parameters and rolling conditions, the search of criteria for assessing the process of rolling of the wheel, the definition of ways to reduce rolling resistance. In 2006, the IF, also called improved flexation, and VF, very high flexation, tires were officially approved by the European Tire and Rim Technical Organization. Today, IF and VF tires have world-known brands producing agricultural tires such as Michelin, Firestone, Goodyear, etc. Such tires have a number of advantages, in particular roller resistance, up to 20% more tangential traction force at the same slip, and so on. The research goal of the paper is improving the efficiency of the pneumatic wheel of the bridge transport vehicle moving on the aligned compacted track of a constant technological track by substantiating the rational optimal parameters of its tire. A physical object of research was a bridge vehicle developed by our construction team, shown on Figure 1. With a track weight of 3.5 meters, the specified vehicle contains a power truss 1, which is a frame rigidly connected to the left 2 and right 3 platforms. Brackets 4 with wheels 5 are attached to platform 2 and 3. The rotation of the wheels 5 is carried out by means of two motor reducers 6 installed in the middle of the platform 2 and 3 and synchronous mechanisms 7 driving the front and rear wheels 5 from each side. In the upper part of the left platform 2, there is a block cabinet 8 with chassis control devices. Between the front and rear wheels 5 on the lower surface of platform 2 and 3, there are support legs of power jacks 9 for lifting the sides of the vehicle from either side when it turns. On the crossbars of the power truss 1, additional units of the hydraulic system of the vehicle were placed, in particular a tank 10 for hydraulic fluid, an electric motor 11, driving the hydraulic pump 12, hydraulic directional control valve 13. Also, in the central part of the vehicle, there is a hydraulic linkage 14, which is borrowed from a serial wheel tractor. Agricultural machines and implements are coupled with the vehicle by means of the hitch 14. As a criterion for the efficiency of the pneumatic wheel of the bridge transport energy vehicle was taken the traction coefficient of the wheel, which can be determined by the dependence known from the theory of the traction 22 shown on Figure 1. where delta is wheel slip coefficient, Fr rolling resistance of the pneumatic wheel, Fk tangential force of the traction created by the pneumatic wheel. According to the goal of developing technology for the selection of optimal parameters of pneumatic tires of wheels of bridge transport power vehicles, moving along the tracks of constant technological track with a constant vertical load action on the wheel, it is necessary to find a compromise solution by solving the equation of the form shown on figure 2, where D0 is static tire diameter, B0 is tire width, PW air pressure in the tire. Finding the extremum of parameters of a bridge transport vehicle tire by solving the partial derivatives of picture 2 of the efficiency function at constant load acting on the tire allows us to determine the minimum tire width B0, the optimal diameter D0, and its air pressure Pw at which the value of Nk will be maximum. In the process of experimental studies, the rolling resistance force of the wheel of a transport vehicle on the traces of a constant technological track was determined by the principle of free movement on the supporting surface. The specified free movement of the vehicle along the traces of the permanent technological track was carried out by its forced movement with the help of a traction mechanism shown in figure 2. The laboratory complex consisted on a bridge transport vehicle 1, the wheels of which freely rolled along the formed track 2 of the permanent technological track. The free movement of the transport vehicle 1 along the track 2 of the permanent tram lines was carried out with the help of the traction mechanism 3, the cable 4 of which was attached to it. The amount of force that was applied to the free movement of the transport vehicle 1 on the tracks 2 of the permanent technological track was recorded on the scale of the dynamometer 5. Revolutions of one of the driving wheels of the transport vehicle were recorded using a special device containing two reed sensors shown in figure 3. The angular velocity of the drive wheel on the transport vehicle was found from the expression equation 3, where Nk, number of transport vehicle wheel revolution, C-1, was determined as follows, where Njk, the total number of pulses received from the wheel sensor of the drive wheels of the vehicle for the time Tjk. Considering picture 5, the operation speed of the vehicle was determined at picture 6. To carry out theoretical studies on a pneumatic wheeled propulsor of a bridge transport vehicle, which moves along the horizontal compacted deformed bearing surface of the cell track of a constant technological track, we presented in the form of an equivalent scheme on which we reflect the forces acting on it, as shown on figure 4. At uniform rolling of elastic tire of bridge transport vehicle on horizontal deformed bearing surface of constant technological track, energy transferred to the wheel is spent for three types of work. These works make up the total rolling resistance energy of the wheel to the bridge transport vehicle: vertical crushing of the soil, elastic deformation of the soil, causing internal friction in the tire, and friction of the tire tread against the supporting surface at the point of contact. The balance equation of rolling resistance forces of the wheel of the bridge transport vehicle, in this case, can be written in the following form equation 9. As a result of calculating the expressions, we receive the dependence of the efficiency of the wheel of the transport vehicle of our design, shown in figure 5, which line 1 is shown B0 equals 0.30 meters, and with line 2, 2 minus B0 equals 0.20 meters. The analysis of the graphical dependence in figure 5 allows us to argue that with the same load Gn equals constant on the wheel of the bridge transport vehicle, its efficiency Nk increases with increasing the diameter d0 and width b0 of the wheel. The appearance of this dependence has two characteristic zones of intensity of change of deflection from the argument. The search for a rational optimum d0 showed that the value of the outside diameter of the wheel tire of the bridge power vehicle should be 1.245 meters. The resulting value is taken as the base value of its wheel diameter in further calculations. According to the requirements for the track farming system and the research goal, it is desirable to have the smallest possible tire width B0 of the pneumatic wheel of the transport vehicle. To meet this requirement, consider the relationship between the efficiency coefficient Nk of operation of the wheel of the vehicle and the width B0 of its wheel tires shown on figure 6. The character of the dependence shown in figure 6 also refers to a two-zone in which the curve has a point of rational optimum. In study showed that it falls on the value of the tire width B0 of 0.250 meters. Based on the values obtained for the rational parameters of the vehicle's wheel tires, we selected tire size 9.5 R32 for which D0 equals 1.245 meters and B0 equals 0.241 meters. Because of the possible alternatives of tires with similar parameters, the profile width in the selected tire is minimum, and the coefficient of efficiency Nk of the wheel in this case is maximum. As a result of this research, it was found that when justifying the parameters of tires of wheels of bridge transport vehicles, which move on the traces of a constant technological track, it is necessary to solve a compromise problem. According to it, on the one hand, the width of the tire profile of the power vehicle should be as small as possible, and on the other, the wheel has, in this case, to develop the maximum efficiency of its work. The solution of this problem by analyzing partial derivatives of the coefficient of efficiency function of the wheel of a bridge transport vehicle allows to find points of rational optimums of its pneumatic tire parameters effectively and efficiently. The studies have proved that when selecting the size of the tire for bridge transport vehicles, we should be guided first by the choices of its width and then consider its carrying capacity, its diameter. Studying the rational parameters of pneumatic wheels for bridge transport vehicle has shown that the zone of rational optimum of its tire width falls on the interval 0.20 to 0.30 meters and its diameter 0.90 to 1.25 meters, and that increase of air pressure in wheel tire from 100 kilopascal to 160 kilopascal increases the wheel coefficient of efficiency. The proposed method of optimization by using the traction coefficient of the wheel as an efficiency criterion allows to determine the rational parameters of the projected wheel propulsor of the bridge transport vehicle, which has high efficiency and cost effectiveness. The research allowed to determine the optimal parameters of the wheel at a given vertical load, such as tire width, diameter, air pressure in the tire, and which the drive wheel has the maximum efficiency, or to solve the reverse problem for given dimensions of the wheel to determine the optimal weight load acting on it. The conducted studies have established that when selecting the size of the tire for the bridge transport vehicle, first you should be guided by the choice of its width, the value of which, from the perspective of the minimum width of the permanent technological track, should be as small as possible, and then by its diameter, based on its carrying capacity. Calculations show that according to the criterion of maximum efficiency of the wheel of bridge transport vehicle developed by our construction, the rational optimum of the main parameters of its tire wheels falls on the size of the diameter of 1.245 meters and a width of 0.250 meters. Practical realization of the specified parameters corresponds to the tire size 9.5 R32, the coefficient of performance of which is equal to 0.86. The relatively low value of efficiency is explained by its tractor affiliation. Therefore, justification parameters of the new tire, specifically designed for overhead transport vehicles which move on the track of a constant technological track, is the subject of separate further research. From the perspective of the maximum efficiency of the wheel of the transport vehicle developed by our design with 9.5 R32 tires, it is desirable to set the maximum air pressure in them to 160 kPa in operating condition. It also contributes to the increase of load carrying capacity of tires of overhead transport vehicles. Dear colleagues, thank you for your time.